Okay, so welcome everybody for the second lecture. We are very happy to have Kesav Krishnan from UIUC. Many of you know he was a MAT student at ISI and then he was for some time at IAC and now he's in Urbana, Champaign. And thanks to him for waking up so early or sleeping late, whichever, and giving this talk. Okay, over to you, Kesav.
So thank you for having me here, and it's even though it's virtual, it's good to be back. I've been here I've been attending at the talks many times, and now it's good to be back as a speaker. So I'll get started. So the first thing I'd like to do is define what a Monomer-Dimer model is, or at least introduce the concept. The origins are in statistical mechanics and in statistical physics, where it was first described by Roberts to study the absorption of diatomic molecules or dimers onto a crystal lattice on an underlying, or in other words, an underlying graph. So a mathematical definition for that would be a collection of non-overlapping edges on a graph. So non-overlapping meaning that they don't share a common vertex, and that's better known as a matching. So no two edges in a matching would have a common vertex, and the matching is called perfect if it covers V. And we'll denote the collection of all matchings on a graph by script M. So what is a Monomer-Dimer model? So we want to eventually associate a probability measure to a Monomer-Dimer configuration. So we start by associating an energy or a Hamiltonian to a given configuration. So this is done by assigning weights to the vertices and the edges. And so the vertices will carry the weight nu and the edges will carry the weight omega. And we define the Hamiltonian for a configuration by just summing over the weights of the unpaired vertices and the weights of the edges that are present in the matching. And with those weights in mind, you define a Gibbs probability measure on the space of all matchings, and the probability of a given matching to be selected is proportional to the exponential of the energy of the matching. And over here, Z is the constant of normalization, and it's called the partition function. So the statistics of interest, what we're interested in quantifying later on, are the typical number of edges or the typical number of unpaired vertices, because if you know one, then you'd know the other. And it's easier to talk about the number of unpaired vertices. So we will focus on that and we will denote that by U. And so that tells you the difference between a matching and a non-matching. So notice in the first case, you have three edges that are non-overlapping and they don't touch each other. In fact, that's an example of a perfect matching. And in the figure on the right, you have two edges that are overlapping. So that's the sort of thing we will not be allowing. So the mathematical analysis of this model was spearheaded by Hellman and Lieb in the 70s. And the way they approached this problem was to write down a recurrence relation for the partition function. So suppose you have a graph with weighted edges and vertices, and if you let ZG denote the Monomer-Dimer partition function, you iteratively remove vertices from the graph. So suppose you have U and V in your vertex set, you denote GU and GUV as principal subgraphs obtained on the sequential removal of U and V. And you have this recurrence relationship for the partition function, where it's ZG is written as a sum of two terms. The first term is just the partition function associated to G with the vertex you remove times the weight contributed by the vertex U. So this would be the weight contributed by all matchings that have the vertex U as an unpaired vertex, plus all the collection of all matchings where U is a paired vertex, and you sum over all the edges that U can be paired to. And the recurrence can be used to prove the absence of a phase transition, and as well as in many cases, it can enable you to exactly compute the partition function. So for instance, in the case of a line graph or a complete graph with constant weights, any place, this recurrence will become a 3-term recurrence. And so then it will admit a determinantal formula. So in the line graph, for instance, the partition function can be expressed in terms of the Chebyshev polynomials. In the complete graph, it can be expressed in terms of the Hermite polynomials. And I think it also admits an exact solution in the case of deregular trees.
So in general, is there a determinantal formula?
No, and the reason, so I'll get into the reason for why that is in a moment. So I mean, I'll talk about that a couple of slides down, but the answer is, like, more often than not, you won't be able to find a correct orientation for the graph that will, what this is actually a permanent. And when you want a determinantal formula, you have to weight it correctly so that the orientations match up, and then you can reduce it to a determinant. And in general, you can't do that.
One more question, Keshav.
Yes.
So when you said constant weights, it means both the vertices and edges you give the weight to be constant, same or different?
Yes.
Okay.
The same weight, they don't have to be, the vertex weights don't have to be equal to the edge weights, but they have to be for any 2 vertices, you'd have the same weight, and for any 2 edges, you'd have the same weight.
Okay, thanks.
So the partition function also admits a representation in terms of moments of auxiliary Gaussian random variables. So to every vertex in the graph, you can associate a Gaussian random variable with a prescribed covariance structure. So that's how we do it. So you have, for every vertex V, you have zeta V, and the covariance is given by the weight contributed by the edge that connects U and V. So the diagonal entries are chosen to be arbitrary, positive, and they're chosen in a way that the matrix is positive definite. In other words, that it will actually give you a valid covariance matrix. And you can express the partition function as this expectation of a polynomial. And the reason this works is you can use Wick's formula. In other words, when you expand this polynomial and you take the moments, like, your moments can be expressed pairwise. And the Hellman and Lieb recursion can be recovered using Gaussian integration by parts. So you just, like, take one particular vertex and then you expand along the term that's contributed by that vertex, and then you apply Gaussian integration by parts. So the absence of a phase transition is interesting, because what it shows is that if you have a limiting free energy, that if you look at the log partition function, divide by the number of vertices and take the limit, that will be an analytic function in terms of the weights. And then that shows that you have no phase transition. Phase transitions can be induced in certain situations. So one way of doing that in the case of the Monomer-Dimer model is the introduction of what's called an imitative potential. In other words, you introduce a term in the Hamiltonian to deal with a monomer-dimer pair having greater energy when they're adjacent to each other. So this has been studied by Alberici and Contucci in the context of the complete graph, where over there, of course, all pairs will be adjacent to each other. But what that does is it introduces a monomer phase and a dimer phase, because there'd be a tendency to clump together. And in the other context, where you do see phase behavior, is in the case of what's called the dimer model, where the monomer weight is -infinity. So in other words, you pick configurations that are perfect matchings. So this is widely studied in the context of planar graphs. And this comes back to the point that I was discussing earlier, because when you have planar bipartite graphs, you have something called a Castellan orientation, where you can then express the partition function as a determinant again. And so that enables the exact computation. And that's been widely studied by Castellan, by Kenyon. It's well known that it's been studied for the so-called Arctic Circle phenomena, where if you look at, like, tilings of certain domains, you have these curves inside of which the tiling is ordered, inside of which the tiling is disordered, outside of which it's locked in order. There's a lot of very interesting universality behavior there. But I'm not going to go into that.
What do you mean by phase transitions when the monomer weight is minus infinity?
So over there, for instance, suppose you look at the square lattice and your edges that are horizontally aligned, let's say they contribute a certain weight, and the edges that are vertically aligned, they contribute a certain weight. You have a phase transition in the sense of the number of vertically aligned edges versus the number of horizontally aligned edges.
Okay, so you're just talking about there are different Gibbs measures in that sense.
Yes, yes.
I got confused a bit because earlier you were talking about the analyticity of the partition function. So
there's a breakdown in terms of the analyticity as a function of those weights. But yes, I do mean in this case, like you have several ergodic Gibbs measures, and the Gibbs measure will be a superposition.
I just wanted to clarify.
So the key task in the context of the Monomer-Dimer model is to establish this free energy convergence, because once you establish that, you can essentially calculate all other thermodynamic quantities. And, what was that? Sorry.
No, there was just some random mistake. Continue.
Okay. So why are Monomer-Dimer models studied? So in the context of statistical physics, they can be shown to be either equivalent or related to several models of interest, such as the Ising model with external field. So in fact, in Hellman and Lieb's original paper, they do prove a correspondence between the Monomer-Dimer model with non-zero monomer potential to the Ising model with an external field, and random assignment problems, which is essentially the Monomer-Dimer model on a bipartite graph, on the bipartite complete graph. And also from the computer science point of view, the computation of the partition function is a hard problem. Because, for instance, if you have a bipartite graph with constant weights, it's equivalent to computing the permanent of a 0-1 valued matrix. And this is known to be in this hash-P class. So quick probabilistic algorithms are of interest here, and more. And Alistair Sinclair, for instance, has a lot of write-ups on that problem from that context. So again, like when you're approaching these statistical mechanics questions, it's a sort of natural next step to then ask what happens when your weights are random variables themselves. So the partition function and free energy can have non-trivial limiting behavior. So they will have fluctuations which you would then want to characterize. And for statistics of interest, like for the number of unpaired vertices, we have environmental and ensemble contributions to fluctuations. And you'd want to distinguish the two and characterize both. So to that end, again, Alberici, Contucci, and Mignoni analyzed the Monomer-Dimer model on the complete graph with IID random vertex weights and established an exact solution for the limiting free energy. And the way you do that is you use this Gaussian integral representation for the partition function, and that enables the saddle point argument. So you find a fixed point in terms of that integral. They also did the same thing where instead of now looking at IID vertex weights, they analyze the model on graphs that are random to start with. So something like the Erdős on any locally tree-like graph. So what they do is I think the exact statement is any graph that is locally convergent to a locally tree-like graph. So the Erdős-Renyi graph comes into this framework, as does the Galton-Watson tree. So you again have environmental randomness in that form. And the solution again is expressed in terms of a fixed point argument.
Sorry, so what is the assumption on the distribution in the IID case?
I'll have to go back, but I think they used bounded support. I'm not entirely sure. I'll have to check up on that again.
Okay.
But the methods that are used in these contexts are explicitly tailored for the mean field situation. So they're sort of analogous to this method that's used in the study of spin glasses called the cavity method, where you'd want to express if you look at the Hellman and Lieb recurrence for the partition function, there takes the form of a fixed point, because the removal of one vertex leaves essentially the same system as before. That's not the context that we'll be focusing on. So what we will be dealing with is a situation where, again, your geometry is quite simple because it's essentially one-dimensional, but it still leads to some non-trivial behavior. So we work on what are called cylinder graphs. So in other words, you have an underlying line graph, which I'll refer to as the horizontal layer. And then you'll have a fixed graph, a fixed finite graph H, and I'll be taking the Cartesian product of the two. And we'll work with IID families for the vertex weights and the edge weights. And
very naive question. What is the Cartesian product of graphs?
The vertex set will be the Cartesian product of the individual vertex sets. And then the adjacency relation is prescribed based on suppose you have V1, W1 and V2, W2. These vertices will be adjacent if either V1 and V2 are adjacent or W1 and W2 are adjacent, but not both at the same time.
Oh, okay. Only one of them have to be adjacent.
No, it's more than that. The other two have to be equal. V1 has to be equal.
Oh, right. Yes.
Then W1 has to be adjacent.
Right.
Or the other way.
Okay.
And so the edge weights and the vertex weights don't necessarily have to be from the same distribution, but they are independent. And we'll also require this 2 plus epsilon moment condition. And the reason for that is to establish central limit theorems later on. So this will be the Lyapunov condition that we'll be using. So this is some notation that we'll be following. So whenever you have this, the script GKL will represent the graph that's truncated to a section KL on the underlying line graph. And ZKL will be the partition function associated to GKL. And UKL will denote the number of vertices of a matching M that are then contained in that section GKL. And this is the first theorem that we established. So assuming that you have this finite 2 plus epsilon moment condition, you have a real number F and a positive number sigma F, depending only on the distributions of nu and omega, such that your scaled log partition function converges in probability. And the fluctuations about the scaled log partition function converge to normal distributions, a centered normal distribution with variance sigma F squared. The second result that we establish is more to do with the structure of a typical matching. So where are the unpaired vertices going to be located? So suppose you have a section the section going from 1 to n times t. And you look at the number of unpaired vertices within that section. You have a limiting distribution for that, for the density of unpaired vertices with respect to the section, which I'm going to call U. And the fluctuation about that is going to be given by standard Brownian motion, scaled by a parameter sigma, which I'll describe later. So if you've seen if you've seen the study of the Dimer model on two-dimensional lattices, there's a notion of a height function that's associated to matchings, and it's a slightly non-trivial correspondence that's made. But over here, it's far more trivial because just calculus is easier to do in one dimension. You count the number of vertices that there are within a certain section, and then that describes the derivative of a discrete function. And then you can just integrate over that to get a notion of a height function in 1D. And what we're saying is that our height function converges to just a linear function with slope u.
Keshav, sorry,
Yes.
2 questions. Okay, one is any particular reason for considering cylinder graph? Apart from that, you can get an explicit handle on things.
No, that's actually the only reason. The reason why you want to use this, the one dimensionality will allow you to use subadditivity.
Okay.
And that's quite crucial.
Okay.
That's the mechanism that we'll use to actually prove convergence of the log partition functions. So that's the reason why cylinder graphs are chosen. Initially, the question started with how two-dimensional can we make things, or how we wanted to let that graph H grow with n as well, but you can't really we couldn't really get a handle on that.
Okay.
So the fact that you have a line graph, that helps, is it?
Yes.
Okay. Sorry, Yogesh, you were saying something.
No, sorry. So other thing I wanted to know was that, see, there were 2 constants in your first theorem and 2 in your second theorem. Are these, there is any relation, or the sigma is sigma f in the previous slide, or are these different?
So on a related note, Keshav, in the statement of your main result 1, you have a sigma sub capital F, right? So what is capital F?
The sigma sub capital F, we just denoted that sigma sub capital F because it's the variance of the limiting free energy. So F would just be the free energy there.
I see.
The 2 sigmas are different. Yeah, the 2 sigmas will be different. And in terms of relationship between the constants, there is a relationship between the constant F and the constant U, which I will detail out later. The relationship between the respective sigmas is slightly more complicated.
Okay. Thanks.
So the key ideas for establishing free energy convergence is the one dimensionality of the model. So the Hellman and Lieb recursion can be recast into a form that allows the application of a subadditive theorem. So the new form of the recursion will then enable you to write the free energy and the number of unpaired vertices essentially as sums of IID random variables with an error term that can be controlled in limit. And we will show that this error term vanishes in all relevant limits. So this is the sort of subdivision that we'd be looking at. So you take a central layer of edges and then you discard them and you look at the error that's acquired in the partition function at the partition function level. And then you iteratively continue this process. So the error decomposition is going to follow a bit like this. So let K be fixed, and K denotes a vertex on the underlying line graph. And let the script EK denote the layer of edges joining the section G1K and the section GK plus 1 through n. So those can be enumerated based on the vertices of our vertical section graph, based on the vertices of H. And this is the sort of error term that we start accruing. All you're doing over here is applying the Hellman and Lieb recursion again and again by removing vertices corresponding to that layer one by one. So if you were to explore what this term is, all this is doing is basically counting the contribution to the partition function where one particular edge in that central layer is included. And this is something that can be controlled. So if you look at this expression for the R and K, by an application of the multinomial theorem, you can write this in product form and then expand the log out. And for a good moment condition on omegas and nus, you also get the same moment. You also get the same bounded moment for R and K. So that's what we have. So based on the fact that you have 2 plus epsilon moment for omega and nu, the 2 plus epsilonth moment of R and K is uniformly bounded above, independent of N and of K. And we need an approximate version of the subadditive theorem, not the exact version, and that was proved by Hammersley. So in other words, let AN and BN be sequences where AN is subadditive with an error given by the sequence B. So a sufficient condition for AN to converge is just for the sum of Bn over n squared to be finite. And this is directly applicable now with our error decomposition to both the expectation of log Zn and the variance of log Zn. And once you have that, the central limit theorem will follow from the Lyapunov condition by setting up a triangular array based on this iterative decomposition. So you associate a random variable to every piece that you would get by dyadically subdividing your graph, and that gives you a triangular array to which the Lindeberg-Feller CLT can be applied. So if you recall in my main theorem, I talked about the fact that the limiting variance is non-degenerate. So you have sigma f is strictly greater than 0. And that's something you really require to establish the central limit theorem as well. And the way we prove that is by completing the underlying line graph into a cycle. And the reason you want to do that is because then that brings in translation invariance based on the shifts along the cycle. So there's a martingale argument that we can use to bound the variance of Zn below, bound the variance of log Zn. So if you consider the partition function associated to the situation where the graph is a cycle and you call that Wn, again, you use this Hellman and Lieb recurrence to show that the difference between the log partitions functions is at most bounded by a constant. So if you establish a variance bound for one of them, you've established a variance lower bound for the other. We pick a horizontal layer of edges corresponding to, let's say, one vertex corresponding to H. And you consider a filtration based on the edges that are included in that layer. And then you include one edge at a time to define this filtration Fj. And you can write the variance in terms of the martingale differences. And the last inequality just follows as an application of the Tau property. And once you have that last step, you use the translation invariance to show that the expectation of log Wn given omega j is independent of j. So all you really need to do is show that the variance has a non-trivial dependence on one of the edges. And then that shows you that the total variance is bounded below by a constant times n. So having characterized the limiting behavior of the free energy, we need to then move on to the unpaired vertices. And the way we tackle that is using the trick of exponential tilting. So you reweight the vertices. You add a constant x to every vertex. And the Gibbs average of the number of unpaired vertices can be calculated by taking the x derivative of the log partition function. So if you want to apply the same sort of error decomposition as the free energy to the number of unpaired vertices, if you go back to the error decomposition that we had, if you're taking the x derivative of each term, you then need to control the x derivative of the error term as well. So if you go back to that in the expression of R and K, you had these ratios of partition functions with corresponding edges in that layer excluded. You need to control the derivative of that ratio. And just by controlling the first derivative of the ratio is equivalent to controlling the derivative of the difference of the logs. So the idea here is going to be to use the zeros of this function that we've described in terms of x. So the partition function is actually a polynomial in e to the x, and it's going to have purely imaginary roots. And the way you can do that is by applying the recursion again and again. The graph on two vertices is going to have a partition function with two imaginary roots. Oh, I'm sorry. Can everyone still hear me?
Yes.
Yes.
It appeared there was an issue in the chat.
Yeah, I lost you for about a minute. You were like the screen was frozen.
Oh, okay.
But now it's okay.
Okay. So then by an inductive argument, you can actually show that the vertices are the zeros of that polynomial are going to be purely imaginary. And they also interlace each other. So that's the sort of picture that we're expecting. So in other words, if you have one vertex removed, if you look at the principal subgraph corresponding to the removal of that vertex, and you look at the Li-Yang zeros of the corresponding partition function, you have this interlacing property that is reminiscent of the interlacing that, for instance, submatrices of a matrix that follows. The eigenvalues of a submatrix interlace the eigenvalues of the larger matrix. So all our relevant thermodynamic quantities eventually will be evaluated at x equals 0 to recover our original measure. So that's what the interlacing looks like graphically. So suppose you have a graph on 5 vertices and you look at the Monomer-Dimer partition function. Notice that like whenever you have an odd number of vertices, you will always have a Li-Yang zero situated at 0, corresponding to the fact that you can never have an all-dimer configuration. And the Li-Yang zeros of the layer below are always situated between two zeros of the layer above. So the average number of unpaired vertices, the Gibbs average of the number of unpaired vertices, can be expressed in terms of these zeros just by taking the derivative. And using the interlacing, you can also control the effect of the removal of a single vertex. So you can control what happens to that average, and you can show that the effect of removing a single vertex has the effect of changing the average by a factor that's at most bounded by a constant. And this can be finitely iterated to yield a constant order bound for the derivative of your error term. The subadditive lemma then applies to the Gibbs average of the number of unpaired vertices, and then you have a limit for that as well. So again, we need to, in order to move further, so now we've established the convergence of the average number of unpaired vertices. What we can now do is use that convergence to establish the convergence of all the higher cumulants as well. So in other words, the variance of the number of unpaired vertices and the third cumulant and so on. What we do is consider the empirical measure associated to the Liang zeros. And the free energy of our model, as well as the number of unpaired vertices, can be written in terms of this empirical measure. The sequence of empirical measures in terms of n is a tight sequence, and that follows from the tightness of the weights. Notice that we don't expect a moment condition for the exponential of omega or the exponential of the news, but we do expect them to be tight random variables. The convergence of the average number of unpaired vertices actually implies weak convergence in probability of this sequence of measures. And the reason for that is, if you look at this integral, it's oddly similar to the Stircher's transform, and we know that a Stircher's transform determines the measure. And in fact, it is a Stircher's transform, except for the fact that the lambda is squared. I neglected to mention earlier, the reason why that's not a problem is the fact that it's because your roots are purely imaginary and your partition function is real. That means they're conjugate pairs of each other. So they're symmetric about 0. So in other words, this function can actually determine the measure. So you have the convergence of this empirical measure. And if you wanted the quenched variance, for instance, all you would have to do is to take the derivative of this expression, of the expression of the number of average vertices with respect to x. And then you're still integrating a bounded function with respect to a probability measure. So in other words, if rho n is weakly convergent, the integral converges as well. So weak convergence of rho n implies convergence of all quenched moments of u divided by n. And we denote the limiting variance as sigma q squared. So the boundedness of the third cumulant of u divided by n is particularly useful for proving central limit theorems, and we'll see that in a moment. So we've characterized what the variance of u looks like, what the quenched variance looks like. Now what we want to do is characterize the fluctuations as well. And to that end, we consider the generating function of u. And what you can show is that if you look at the log of the generating function, it has this neat expression in terms of just shifting the parameter x by a small factor, by just looking at the difference of what happens when you shift that parameter x. And you can apply Taylor's theorem because all our derivative terms are bounded. So it shows that the limit of the log generating function of the scaled number of unpaired vertices is just going to be sigma squared times a quadratic term, which then implies that it converges in distribution to a Gaussian. But now we need to factor in the environmental contributions to the fluctuations as well. So notice that the Gibbs average of the number of unpaired vertices is itself a random variable. So this overline notation then denotes the centered Gibbs average with respect to the environment. You can use the Efronstein inequality. In fact, I should have mentioned this earlier because this is also used to prove the convergence of the average of u divided by n. The Efronstein inequality shows that the variance of u is bounded above by a constant times n. this sequence the sequence of averaged, the sequence of variances is also approximately subadditive. We have a limit of the variance of u divided by n. And you can use the same Lindeberg-Feller argument that was used for the free energy for the number of unpaired vertices in each of these pieces. And just for a moment, like I should just mention, so the expression sigma squared q and for the number of unpaired vertices, that can be written in terms of this limiting empirical measure. So I remember there was a question earlier on as to what the relationship between the constants was. The free energy is the limit of this function, the integral of log e to the 2x plus lambda squared with respect to this empirical measure. The average number of unpaired vertices, in other words, the constant little u, is the limit of the integral of e to the 2x over e to the 2x plus lambda squared. And this quenched variance sigma q squared, that will be the limit of the derivative of this function. On the other hand, we don't really have a clean expression for the limit for what sigma squared a is. We do provide bounds, but we can't provide a closed form expression. And that's analogous to the fact that we don't really have a closed form expression for sigma f either. So now we look at what the behavior is across disjoint pieces. In other words, how do unpaired vertices interact with each other? So we consider disjoint sections, and because as a consequence of the fact that the weights are independent across disjoint sections, the averages, the Gibbs average on section 1 through k and the Gibbs average on section k plus 1 through n, those are independent of each other. So in particular, by this central limit theorem that we've already established, you get this joint central limit theorem for free. The exponential tilting argument can be adapted to study the number of vertices that correspond to individual sections as well. So you tilt the vertices in section 1 through k by x1. You tilt those in section k plus 1 through n by x2. x1 derivatives of the log free energy will tell you how many vertices there are in the first section. x2 derivatives will tell you how many there are in the second section. Mixed cumulants are provided then by mixed derivatives. And the Quench-CLT method can then, the same method is applied now to the log partition function as a function of those two variables, and you just use the multivariable Taylor expansion. So you get the convergence to a joint Gaussian for those disjoint sections as well, where the variance now is sigma q squared. And importantly, the quenched and the annealed fluctuations are independent in the limit. We're now in a position to characterize what a typical matching looks like. So what we can show is that if you look at the average number of unpaired vertices in a section, that differs from n times u by at most a constant. So it implies immediately that if you look at the scaled number of unpaired vertices corresponding to the section 1 through nt, that's going to converge to this linear function that we discussed earlier. The joint CLT, the method that we just used to establish the joint CLT for two pieces, can be finitely iterated for any number of pieces. So that is sufficient then to establish independent Gaussian increments with the correct covariance structure of Brownian motion. And the sigma squared over here is going to be the sum of sigma q squared and sigma a squared. The process level convergence is yet to be shown. And for that, I think we need a little more control on the covariance structure. And just to wrap up, I thought I'd show some connections to the theory of random tridiagonal matrices. So over here, suppose you take H to be a single vertex, your Hellman and Lieb recurrence will become a two-step recurrence. In other words, you have log of Zn corresponds to some constant plus times log of Zn minus 1 plus some constant times log of Zn minus 2. And that suggests an expression in terms of the determinant of a tridiagonal matrix. And you can indeed do that. So if you look at this matrix over here, where you have e to the vertex weights, but over here the edge weights are divided by 2. And that's important, like, when you expand the determinant, the off-diagonal terms get squared. Turns out that the partition function can be written as the absolute value of the determinant of this matrix. And the Liang zeros correspond to eigenvalues. So in the one-dimensional context, you do have a determinantal formula, and that can be used to prove a lot of our results and vice versa. So in particular, the convergence of the free energy is analogous to the convergence of the so-called Lyapunov exponent of these tridiagonal operators. And the fact that you can, when the weights are bounded, you can use the Lyapunov exponent to show that the empirical spectral measure of the matrix converges. That's something called the Thouless formula. Our result for the convergence of the free energy is analogous to that. So I'll stop here. But thank you for coming in, and thank you for listening.
Thanks, Keshav. So before opening up for questions, let me ask people to unmute and applaud Keshav.